So in this video I'm going to talk to you about the Doppler effect, which is named after an Austrian physicist called Christian Doppler, and at the end of the video we'll talk about how it links to space physics and why it's important. So let's have a quick recap about waves, because the Doppler effect is to do with waves. So we should know that a wave will have a wavelength and it moves through space with a given speed, and that it also has a frequency, which is the number of waves that you see or observe per second. We should also remember that the wave velocity is equal to the frequency times the wavelength, and also that the time taken for one wave is t, which is equal to 1 over the frequency. It's this equation that's the most relevant today. So the wave speed, the wave frequency and the wavelength are all linked to each other. If one changes, then at least one of the others has to change. If we look at waves from the top down, these might be ripples in water, then they spread out in these directions like so. So when we draw the direction of waves, what we're actually doing is drawing a line at 90 degrees to the wave fronts, and the wave fronts are the peaks or the troughs of the wave. Okay, so these white lines correspond to the peaks and the dark blue lines correspond to the troughs of the wave, and as the wave moves outwards, or just moves, then the direction of that is determined by the arrow, which is at 90 degrees to these lines here, which we call the wave fronts. The distance from here to here and the distance from there to there is the same, and that's the wavelength of the wave, which you can see from this here. So that is one wavelength, that's another wavelength. If I was to stand here and count the number of waves that go past every second, that would give me the frequency, and that would be linked to how fast the wave was travelling in that direction and the wavelength. Okay, again linked to this equation, v equals f times lambda, so the frequency would be equal to the wave speed over the wavelength. And that would be the same everywhere. So if I was over this side observing the same waves, then because they're travelling at the same speed and have the same wavelength, they would appear to have the same frequency. Things get a little bit different if the source of the wave is moving. So instead of dropping a stone into the water and creating ripples that spread out, if there was something that was moving creating those ripples, for example a duck bobbing up and down on the surface of the water. Here we've got a little simulation of a duck on water, and the duck's bobbing up and down creating ripples which are spreading out in all directions at the same velocity. And again, if I was to stand here, then I'd observe those waves at the same frequency as if I was to stand here, because the wave speed and the wavelength are the same. If, however, the duck is moving, you'll see the waves in front become closer together and the waves behind become further apart. So the wavelength is effectively decreased, and that's because the duck moves forward in the time it takes before the next wave is made, and so it catches up with the previous wave a little bit. And the faster the duck goes relative to the speed of the wave, the closer those waves get together. So if the duck were to go really fast, you can see the wavelength now in front of the duck, or in front of the direction it's travelling, is very, very small, and the wavelength behind the duck has increased significantly. Now the waves are travelling at the same speed in all directions, but the wavelength has changed. So where the wavelength has reduced, according to our equation, the frequency must have increased. And conversely, where the wavelength decreases, the frequency must have decreased, because the wave speed is the same. Right, so the Doppler effect is the apparent shift in frequency of a wave due to either the source or the thing that's observing the wave moving. It doesn't matter if it's the thing that's producing the wave moving or the thing that's observing it moving towards or away from it. As long as they're moving relative to each other, then you get this apparent shift in wavelength or frequency. So that gives us a very common effect that you may have heard, which is most notable for racing cars because they're travelling particularly quick relative to the speed of sound. So as a racing car comes towards you, it's catching up with its own sound waves, and so the frequency sounds higher. Then as it drives away from you, the frequency drops. I'll play you a little clip now. There's a few gear changes in that audio, but you should have heard, there was 2 cars went past, but you should have heard the pitch of the sound drop noticeably as the car went past. We also know that light is a wave. So water ripples are a wave, sound is a wave, light is a wave. So why do we not see the Doppler effect with light? Well, the speed of light is approximately 1,000,000 times faster than the speed of sound. And so the object needs to be moving at near the speed of light, or a significant fraction of the speed of light, in order to observe it. So if you could drive your car at, I don't know, 150 million meters per second, half the speed of light, then the headlights, as it was coming towards you, would appear to be a slightly different colour to their normal colour. And this effect is observable in space. When we look at distant galaxies, we see that the light has changed frequency slightly. We'll look at that in a lot more detail next lesson.